Good evening, ladies and gentlemen. Today, we will be presenting our production metallurgy assignment. The presentation focuses on the manufacturing of titanium turbine blades with a particular emphasis on comparing additive manufacturing and powder metallurgy. We will also explain why additive manufacturing, specifically laser powder bed fusion, is the most suitable method for producing lightweight titanium blades with internal cooling channels. In the background and motivation, titanium alloys combine low density, high specific strength, good corrosion resistance, and high temperature performance. These properties makes it favorable for aerospace, which includes blades, structural parts, and compressors, and marine application. Turbine blades are rotating vanes in gas and steam turbines that take energy from hot, high-velocity steams. They operate under extreme mechanical loads, high temperatures, and corrosive environments. According to Movara et al. 2025, turbine shafts require a material that can withstand such conditions to ensure safety, low maintenance cost, and longer lifespan. They also require a suitable manufacturing process, which is suitable for manufacturing complex shapes with minimal defects. They are mostly manufactured by casting, particularly investment casting, additive manufacturing. I will pass it to the next speaker.
Greetings, everyone. My name is Banze PS, and I'll be taking you through the main production processes that are being looked into under this assignment, which is powder metallurgy and additive manufacturing. We will start with additive manufacturing. Additive manufacturing is a process that builds parts layer by layer from digital models. The principal additive manufacturing methods for aerospace are powder bed fusion, particularly laser electron beam, and direct energy deposition. This allows complexity and part consolidation that are difficult or impossible with casting or forging. It also minimizes part count by consolidation, enables topology optimization and repair of expensive components. It faces challenges that include microstructural heterogeneity, residual stresses, porosity, and defects that have a negative impact on fatigue and grip performance. Following now, we will look into powder metallurgy. It is a group of solid-state manufacturing techniques in which metal powders are blended, compacted, and sited to produce near-net shape components. It enables controlled composition, integration of reinforcement, and efficient material use for complex shapes. Its advantages for aerospace components is that it allows tailored microstructures, high material utilization, and production of materials difficult to cast. Its limits include achieving full density without residual porosity, controlling contamination or oxygen pickup, and meet strict mechanical properties and certification requirements for safety critical parts, and faces difficulties for complex shapes like turbine blades. I'll pass it to the next speaker.
To produce a lightweight titanium turbine blade with internal cooling channels, additive manufacturing, specifically laser powder bed fusion, is the most suitable method. This is because additive manufacturing can create complex internal passages that powder metallurgy cannot. It also offers high microstructural refinement, high density, and strong mechanical properties. Powder metallurgy requires tooling and cannot easily create hollow or intricate shapes. Thus, additive manufacturing provides the best combination of design freedom, accuracy, and performance. Although powder metallurgy can produce near-net shaped parts, its geometric limitations and the need for post-processing makes it less suitable for highly complex aerospace blades. Additive manufacturing is therefore justified due to its superior design freedom, high quality microstructures, and reduced need for tooling, which makes it cost efficient for low volume, high complexity aerospace components. Thank you. I'll pass it to the next speaker.
Greetings to you all. I'm Member Azeza. I'll be taking you through additive manufacturing process. The additive manufacturing process flow begins with titanium alloy powder production, followed by powder sieving and controlled storage to avoid oxygen contamination. Powder spreading and laser melting then occur layer by layer according to the digital CAD model, enabling the formation of internal channels that cannot be machined conventionally. After the build is complete, the part is cooled in an inert environment and removed from the build blade. Then after the build, the part is subjected to post-processing, which includes the heat treatment for stress relief, hot isostatic pressure to close residual porosity, surface finish to ensure aerodynamic smoothness, and precision machining for dimensional accuracy. The final inspection involves a non-destructive evaluation and dimensional verification to ensure compliance with aerospace specification. Next page. Next page, please. I will also take you through additive manufacturing defects and parameter control, which are preventative techniques. The additive manufacturing defects experience defects such as porosity, cracking, and distortion. Porosity occurs from insufficient melting, unstable melt pools, or trapped gases, which weakens fatigue resistance. Then cracking is caused by the steep thermal gradients, typically in titanium alloy printing, while distortion results in residual stresses accumulation during rapid melt and cooling. Then the parameter control, which are preventative techniques, include optimizing energy density, increase preheatment to reduce thermal gradient, ensure consistent powder quality, and incorporate effective support structures. These measures directly target the source of defect and therefore enhance component reliability. I will hand it over to Mr. Ngwanyana, who will take us through question 2.
Greeting everyone. I'm Ngwanyana Les. I'll take you through question 2. Whereby we're looking at the main powder production method used in powder metallurgy. Firstly, we have gas atomization, whereby we're looking at the molten metal being broken into droplets using the higher pressure inert gas. Produce spherical powder with excellent flexibility and narrow particle size distribution, ideal for AM and PM. So lower contamination risk. And secondly, we have water atomization, whereby we're looking at the molten metal disintegrated by higher velocity water jets, produce irregular angular particles, higher green strength during PM compaction, and the most cost-effective but a higher oxidation risk. Thirdly, we have the mechanical milling, whereby we're looking at the higher energy ball milling, repeatedly fracture, and coast weld particles. And we have produced fine, irregular, or composite powder. It's useful for alloys that cannot be made by melting, and lower flowability, less suitable to AM powder spreading. Thank you for the opportunity, and I would like to give an opportunity to our next speaker, Zulu.
Greetings, everyone. My name is Zulu SM, and I'll be going through steps that are involved in powder metallurgy processing. The first step includes powder production. This is where we create the metal powders, usually through processes such as atomization or biomechanical milling. In this process, key points such as the size, shape, and purity of these powders, they matter a lot because they determine how well the rest of the process will perform and what properties we will get at the end. The second stage being powder blending. Once the powders are produced, they get blended or mixed with alloying elements. Such also this includes lubricants and other additives. The goal here is simple, is to make sure that there is proper homogeneity in terms of composition and there's a smooth flow of the powders. The third process includes compaction. This is where the real shaping normally begins. We press the blended powder in a die under very high pressure to form what we call a grain compact. It is not yet fully strong, but it holds the shape. And how strong this grain compact is depends on the powder size, powder shape, and how much pressure we apply. The fourth stage being sintering. The compact goes into a sinter furnace where they get heated up along the melting point, allowing the particles to bond through diffusion. At this moment, this is where the part gains strength, density, and durability. We also use a controlled atmosphere to prevent oxidation and keep the material clean and strong. The fifth stage being secondary operations. Depending on what the final product needs, we might add secondary operation, which justifies the fact that it is optional. These secondary operations, they include machining, sizing, coining to get perfect dimensions. Sometimes we do heat treatment to improve strength or impregnation and infiltration to add lubrication or raise densities. The last part being the final product. After all these steps, we get a finished product, strong, compact, and shaped exactly the way we need it. I thank you.
Good evening,
Handing over to
everyone.
the next speaker.
Good evening, everyone. My name is Makubela WM, and I'll be taking you through question 3, whereby we'll be discussing additive manufacturing defects, the effects, and how to minimize them. Now, we all know that materials sometimes have a lifespan whereby the defects directly affect their performance and reliability in aerospace components. Defects that we can encounter or that we may come up with in additive manufacturing are porosity, cracking, and distortion, whereby all this affect the performance and they are as follow. We have lower fatigue life, we have reduced strength and causes dimensional inaccuracy. Now, we know that several process parameters can be adjusted to reduce this effect, whereby we can increase energy input to avoid lack of fusion porosity, preheat the plate to reduce thermal stresses, optimize scan strategies, control layer thickness and powder flowability. Now, we also have a suitable non-destructive testing technique for additive manufacturing component, which is X-ray computed tomography. It is the ideal one because it detects internal pores, cracks, lack of fusion defects, and dimensional deviation without damaging the part. For the turbine, for the turbine blades, the computed tomography is therefore the most reliable inspection method for complex additive manufacturing components. And we also have the references provided I thank you.